Hello friends, after seeing the synthesis and reactions of naphthalene, today we are going to see the synthesis and reactions of anthracene. So let us start with synthesis and reactions of anthracene. So anthracene is the next polyaromatic compound after naphthalene. Okay. Let us see the numbering and resonance. As we discussed earlier, the right-hand side topmost carbon gets carbon number 1 when there is no substituent present. And that is what has happened over here. 1, 2, 3, 4. We don't number the junction carbons, and so these carbons are left aside. Now, after numbering this right-hand side ring, if we number this as number 5, then 6, 7, 8, 9, that will not be appropriate because we are not numbering the carbons of same ring in continuation. Okay, and we cannot jump from here to here and then go over here. So what we are doing, 1, 2, 3, 4, then leave aside the central ring, 5, 6, 7, 8. Now two rings are complete, and now only two carbons of the central ring are to be numbered. So 9 and 10. Since this is 8, this will be 9 and this will be 10. Okay. Once again, 1, 2, 3, 4. Don't number the junction carbon. Don't go to here because from here we cannot jump over here when these carbons are left unnumbered. So 1, 2, 3, 4, then 5, 6, 7, 8, then 9 and then 10. Now going to resonance in anthracene. As you can see, anthracene contains 3 rings. In case of naphthalene, we saw the Fry's rule, that is, number of rings plus 1 are resonating structures. So here, the total number of resonating structures will be 3 plus 1, that is 4. Now, let us try to write the resonating structures. In the first structure, the left-hand side ring and the central ring are in benzenoid form because this double bond is common to both the rings. Okay. Then the third ring, that is the right-hand side ring, is not in the benzenoid form. In this case, the second structure, the central ring and the right-hand side ring are in benzenoid form. This one is not. But look at the other two structures. The other two structures, only one ring is in the benzenoid form, either this one or this one. And so the first two structures are more stable because they have two rings in the benzenoid form. The third and the fourth structure are less stable. Okay. Now, coming to synthesis of anthracene. There are 4 different methods for synthesis. The first one is Friedel-Crafts alkylation. I think everybody is familiar with the reaction Friedel-Crafts alkylation. Just see its application in case of benzene, anthracene. Okay, this is benzyl chloride, another molecule of benzyl chloride. What Friedel-Crafts alkylation does is it attaches the aliphatic carbon to the aromatic carbon, right? So Cl is removed with AlCl3 and the aliphatic carbon is attached to aromatic carbon. Similarly, this aliphatic carbon will be attached to this aromatic carbon, and therefore the resultant product will be 9, 10. What happened to this laser pointer? So the resultant product is 9,10 dihydroanthracene. Now what we need to do? We need to convert this to anthracene, and dehydrogenation occurs using palladium and carbon. Okay. The second method of Friedel-Crafts alkylation is you take benzene and you take dibromomethane. Now, what happens in case of one molecule of benzene reacts with one molecule of dibromomethane, one Br will be lost, and what you will get will be benzyl bromide, right? You will get benzyl bromide. This benzyl bromide, another molecule reacts with another molecule of benzyl bromide. So actually, this reaction is same to the first reaction. The only difference being the starting materials are slightly different. Then, when these are fused together in presence of a Lewis acid, they give 9,10-dihydroanthracene, which is then converted to anthracene using palladium and carbon. Okay. Now coming to the second method of synthesis, and that is from phthalic anhydride. We had seen the method of synthesis from phthalic anhydride and from succinic anhydride for naphthalene. Okay. So similarly, this is a Haworth synthesis where benzene reacts with phthalic anhydride. Like acid chlorides, you know that anhydrides also react with benzene in Friedel-Crafts acylation reaction. Okay, so this carbonyl-carbon acylation meaning carbonyl-carbon getting attached to aromatic nucleus. So this carbonyl-carbon gets attached to aromatic nucleus, a ketone is formed, and this COH is left. Now our target is anthracene. So what we need to do? We first need to fuse this. And this reaction you are familiar with. In case of naphthalene, you have seen this. So either H2SO4, where this will get converted to a good leaving group, it will leave, and a bond between carbonyl and this will be formed, or polyphosphoric acid will also do. Okay, so this results in formation of anthraquinone. And this anthraquinone, when distilled with zinc dust, gets converted to anthracene. So, up till now, we have seen two methods, Friedel-Crafts alkylation, and second is Haworth synthesis. But Haworth synthesis is a combination of Friedel-Crafts acylation and some other reaction. Now, the next one is ELB reaction. This reaction is of diaryl ketone containing orthomethyl or methylene group. Look at this. This is orthomethyl benzophenone. When this is heated, pyrolysis meaning strong heating. So when this is heated very strongly, water molecule is lost and this gets converted to anthracene. For those who are interested, I have given a mechanism. You start with this arrow. That is why I'm putting number 1 over here. Okay. Start with this arrow. This attacks over here. As a result, this carbon becomes pentavalent. It cannot. So the double bond shifts. As a result, this carbon becomes pentavalent. It cannot. So this double bond also breaks and oxygen retains the electrons. Okay. Now, you can follow the mechanism in this way. Of course, this is not part of your syllabus, but those who are interested can do that. Okay. So this is ELB reaction, that is a ketone pyrolysis. Now, coming to the final reaction, that is Diels-Alder reaction. I think all of you know that Diels-Alder reaction involves reaction of a diene. This is a diene with a dienophile. Okay. Now, when a diene is reacted with dienophile, there are two carbonyl groups over here. So either one of the carbons has become electron deficient, and so the attack of this on this is possible. As a result, this carbon becomes pentavalent. It cannot. So this double bond breaks. Now this carbon is trying to become pentavalent. It cannot. So This breaks because anyways, this carbon was becoming electron deficient, and this results in formation of this. Now, this is not anthraquinone. There is only one double bond. Okay. So this is converted to anthraquinone by treatment with chromium trioxide. Okay. Now just try to understand and remember this, that reduction is a reaction where a double bond is converted to a single bond. Vice versa, when a single bond is converted to a double bond, it corresponds to an oxidation reaction. Therefore, chromium trioxide, an oxidizing agent. This is a trick to remember. Okay, so anthraquinone is formed, and like in the previous reaction where we saw anthraquinone, upon distillation with zinc dust gets converted to anthracene. Similarly, here the anthraquinone that is formed upon distillation with zinc dust gets converted to anthracene. I hope you follow the methods of synthesis, because if you use these methods in an effective way, remembering part will be lesser. Okay. Now, coming to oxidation reactions of anthracene. The first reaction is oxidation reaction. When anthracene is treated with K2Cr2O7 and H2SO4, I think everybody remembers that when you use potassium dichromate for oxidation, the medium needs to be acidic. So K2Cr2O7 and H2SO4. This results in formation of 9,10 anthraquinone. Okay. Now reduction reaction. When anthracene is treated with sodium and ethanol under reflux, it is the central ring which is reduced fast. Why central ring being reduced fast? These two we will see later also. These two are the most reactive positions in most of the reactions. Here in oxidation also, in reduction also. This is 9,10 dihydroanthracene. And the third and the last reaction is that of electrophilic aromatic substitution. But before that, let us try to understand that resonance energy of anthracene is lesser than that of benzene. Benzene has two exactly equal resonating forms. That is not so, plus there are two resonating forms which are less stable. Okay, and so resonance energy of anthracene is lesser than that of benzene. Now this results in much less aromatic character of anthracene. Okay. Benzene is aromatic, and one characteristic of benzene that we saw was benzene does not undergo addition reaction, as this results in loss of aromaticity and loss of stabilization due to aromaticity. Instead, benzene undergoes electrophilic aromatic substitution, which retains the aromaticity. Anthracene undergoes both addition as well as electrophilic aromatic substitution because the aromatic character of anthracene is lesser than benzene. So, and additional thing, electrophilic aromatic substitution was so important in case of benzene, important in case of naphthalene, but it is less important in case of anthracene. That is because of two reasons. One is formation of polysubstituted products, which happens because of, along with substitution, addition reaction also takes place. Okay. For both electrophilic aromatic substitution and addition, C9 and C10 are the reactive positions. As I mentioned, C9 and C10 are the positions where most of the reactions happen. Now look at this. We are talking about electrophilic aromatic substitution. Okay. So when electrophilic aromatic substitution occurs, it will be this intermediate that will be formed. This is the most stable of the carbocation because two rings are in benzenoid form. Okay. Then this may finally result in a substitution product, or it may result, when you add one more HZ, it may result in addition product. Okay. So this will be more clear with the examples. First, chlorination. When you chlorinate it with chlorine and CuCl2, you get a substitution product at C9. Okay. Although this is on the central ring, still the numbering remains same because you cannot start numbering from here, then go here and so on. So the numbering here remains same. As against that, when you treat anthracene with chlorine and carbon disulfide, then you get an addition product. Here too, you get an addition product in addition to the substitution product. Similarly, in case of nitration, anthracene, when it is treated with HNO3H2SO4, you get either the substitution product, that is here, okay, that is 9-nitroanthracene, or you get 9,10-dinitro product, which is an addition product. Okay, sometimes you get this also, and in addition you get an addition product. Okay, and that addition product is going to be the one which I had previously drawn. Some Z, anything, any Z. Okay. So with that, we have completed the reactions of anthracene. And now one more instruction is after phenanthrene, I will put all the questions. So wait for phenanthrene, after which there will be questions, practice questions. Thank you.